Welcome to our first module on dynamics. In this module, we focus on emergence. You will learn how to determine which model results emerge from agent simulation experiments and which are imposed and predictable. You will also develop an understanding of what makes the results of ABMs more versus less emergent by looking at two of NetLogo's library models, and you will start using the most important technique in agent-based science, designing and analyzing simulation experiments to test hypotheses and develop understanding about how an ABM works and how well it reproduces the system it models. On the technical side, you will learn how to use behavior space, NetLogo's extremely useful tool for automatically running simulation experiments and producing output from them, and we will analyze the output produced by NetLogo models by importing results to other software for graphing and statistical analysis. Let's go! So, what is emergence? Let's start with a definition. The most important and unique characteristics of ABMs is that complex, often unexpected dynamics at both the individual and system levels emerge from how we model underlying processes. When we give agents rules for adapting to changes in their environment and to what the other agents do, then the behaviors of each agent, and therefore the whole system, emerge from those rules, the characteristics of the agents and the environment. Emergence, therefore, is the most basic concept of agent-based modeling. The key question about emergence is this: what dynamics of the system and its agents emerge, that is, arise in relatively complex and unpredictable ways from what adaptive behaviors of the agents and what characteristics of their environment? In contrast, what other behaviors and model dynamics and outcomes are instead imposed, that is, forced to occur in direct and predictable ways by the model's assumptions? That's what we call imposition. By unpredictable here, we refer to outcomes that are difficult or impossible to predict just by thinking. The concept of emergence has sometimes been given mystic connotations such as being unexplainable in principle, but with ABMs, we are focusing on just the opposite, on explaining things via simulation. So the central question is, can you make your model or your system look and behave like the real one by equipping your agents with the right adaptive behaviors? There is no simple way to classify some particular outcome of an ABM as emergent versus imposed, but we can think about these qualitative criteria for a model result being emergent. It is not simply the sum of the properties of the model's individuals. It is a different type of result than individual level properties or decisions, and it cannot easily be predicted from the properties of the individuals. Now let's see how these three criteria apply to the butterfly model. The first step is to identify the specific model outcomes we're considering. The specific numerical results of the butterfly model that we've been focusing on are the widths of corridors that groups of hill-topping butterflies use as they migrate. These outcomes result obviously from the one decision that model butterflies make, whether to move uphill or randomly at each time step. So, do the butterfly model's corridor width results meet the three criteria for being emergent? Number one, corridor width is not simply the sum of individual butterfly properties and is a different type of property from the properties of individuals. The individual butterflies have only one property, their location, and the width of a migration corridor is a different property than the location of an individual. And remember that we discovered earlier that butterfly corridors changed qualitatively when we switched from a simple artificial landscape to a realistically complex landscape. So corridor width emerges from the environment as well as from butterfly behavior. On the other hand, we must admit that the corridor width of a group of butterflies is, in a way, just the sum over time of where the individual butterflies were. So we can answer the first question with a definite yes and no, or sort of. Number two, we are looking for a different type of result than individual level properties or decisions. We know that in our current model, individual butterflies have only one property, their location. The width of a migration corridor, though, is a different property than the location of an individual, and it is measured differently. So we can answer this question with yes. Lastly, is corridor width then easily predicted from the properties of the individuals? Not completely. But even without the model, we would expect corridor width to decrease as the value of the parameter q, which remember is the probability of the butterfly moving directly uphill instead of randomly, increases, and to get very large as q approaches 0. So we could describe the butterfly migration model as having its key outcome emerge from the individual decision of whether to move uphill or randomly and from the landscape. But because this behavior is so simple, there is at least one model result, how corridor width varies with q, that is really quite predictable. The behavior of individual butterflies is also largely imposed. We can predict how often one will move uphill or randomly just from q, instead of having this behavior emerge from a complex submodel that considers, for example, how steep the hill is or where food or where other butterflies are. So the right answer here would be really no. So here are the results of our investigation whether the butterfly model follows the 3 criteria for emergence. Number 1, the key outcome emerges from the individual decision of whether to move uphill or randomly and from the landscape. So 2 factors, but those 2 factors are still pretty limited. Number 2, how the corridor width varies with q is predictable. So we really don't satisfy the criterion of non-predictability. And in addition, the behavior of individual butterflies is also largely imposed. We can predict how often one will move uphill or randomly just from q. Now, the extent to which ABM results are emergent can vary widely, and having more emergence does not necessarily make a model better. The best level of emergence is often intermediate, kind of what we're seeing here. Models with highly imposed results are often not very interesting because their problem can often be solved with a simple mathematical model. On the other hand, a model with too many of its results emerging in complex ways from too many complex individual behaviors and mechanisms can be very hard to understand and learn from. The butterfly model is not a bad ABM just because some of its results are not surprising. It is a perfect model for the problem it was designed for. But that problem did not involve highly complex agent behavior. To make the model more interesting, we should consider building a complex submodel that looks at how steep the hill is or where food or other butterflies are. That way, we get more criteria that may lead to a better idea of emergence. So now let's look at a model with a low degree of emergence. The biology category of NetLogos Models library includes a model called Simple Birth Rates. It is indeed a very simple model designed to simulate how the difference in birth rates between 2 co-occurring species, the red and blue turtles, affects the number of individuals in each population. The 2 species differ only in the number of offspring each individual produces each time step. The probability of death is the same for both species and is adjusted so that the total number of individuals is approximately constant. Take a look at the description right here, and then open this model, read the Info tab, and play with it a little bit. Let's focus on one question that this model can address. How does the time until extinction of one species depend on the relative birth rates of the two species? If we hold the birth rate of the red species, that's the global variable red fertility here, constant at, say, 2.0, and vary the blue fertility from 2.1 to 5.0, how does the number of ticks until extinction of the red species change? To answer this question, this model includes a button and procedure called Run Experiment. The Run Experiment button runs the model until one species is extinct. It tells us how long it took, and then it starts another run. Try it yourself. If we think about this problem for a minute, we can form a pretty strong expectation of the answer. When birth rates of the two species are close, they should coexist for a long time. As the difference in birth rates increases, the time to red extinction should decrease rapidly. But no matter how rapidly the blue reproduce, it seems unlikely that the reds will go extinct immediately, because the model is initialized with 500 of them. So the time to red extinction will probably never get as low as one time step. We thus expect the fertility curve to start high when blue fertility is 2.1, drop rapidly, and then flatten out at a value above 1 as blue fertility increases. Are these expectations correct? Well, to find out, we need to do a simulation experiment. To see how the time to extinction of red turtles in the simple birth rates model varies with the fertility parameter of blue turtles, we need to run the model over a wide range of blue fertility values and record the time, or the tick number, at which the number of red turtles reaches 0. But there's a complication. This model, like most ABMs, is stochastic, producing different results each time we run it because the turtles that die each tick are chosen randomly. Check out the Grim Reaper procedure in the bottom right corner here. Because the model produces different results each run, to really understand it, we need to estimate the average results and the variability around these averages. Modelers often do this the way that scientists study real systems that are highly variable, by executing experiments that include replicates of several different scenarios. Before we go any further, let's define a couple of terms. In simulation modeling, a scenario is defined by a model and one set of parameters, inputs, and initial conditions. If a model has no stochastic elements, it produces exactly the same results each time it executes the same scenario. Replicates are model runs in which only the stochastic elements of the model change. To be specific, replicates usually refer to model runs among which only the random numbers differ. And there are also other ways to replicate model scenarios, and those can be by randomizing input data or by randomizing the initial conditions. Now, to analyze how blue fertility affects the time to extinction of red turtles, we will use a simulation experiment that varies blue fertility from 2.1 to 5.0 in increments of 0.1, producing a total of 30 scenarios. Further, we will run 10 replicates of each scenario. Each model run will continue until there are no more red turtles, and then will output the tick number at which this extinction occurs. These results need to be recorded in a file that we can then import to a spreadsheet or statistical software and finally calculate the mean and standard deviation of time to red extinction, and graph how they vary by blue fertility. This is an example of a sensitivity experiment, a simulation experiment in which we vary one parameter over a wide range and see how the model responds to it. This experimental design is very useful for understanding how a model and the system it represents responds to one factor at a time. In order to automate experimental runs, rather than setting each run up by hand, we use the Behavior Space plugin in NetLogo. Behavior Space runs simulation experiments on your model and saves the results in a file for you to analyze. By filling in a simple dialog, you can program it to create scenarios by changing the value of global variables, generate replicates of each scenario, collect results from each model run and write them to a file, determine when to stop each model run, and run some NetLogo commands at the end of each model run. In the Behavior Space dialog, you can create new experiments, edit previously saved ones, or copy or delete experiments for the same model. More about that later. When Behavior Space has finished running the experiment, you can import the results to the software of your choice, calculate the mean and standard deviation over the 10 replicates of the time to red extinction for each value of blue fertility, and draw a graph like what you're seeing here, which I built with pivot tables in Microsoft Excel. So, does this graph look like we expected it to? While it seems reassuring that the model produced results that were quite as we expected, it also makes us wonder what the value of building an ABM was if it produces results we could easily anticipate. In fact, we chose this model to examine first because it is a clear example of an ABM whose dynamics are strongly imposed by its very simple, rigid agent behaviors. The agents make no decisions. They have no individual state variables, and their very few behaviors, reproducing or dying, are tightly specified or imposed by the global parameters. Also, the model is non-spatial because agent location has no effect. So if the agents in this model adapted their fertility to, for example, local density or other turtles or food, or had to find mates within a certain time or distance before reproducing, the model would produce less predictable and more interesting results. While this model is fun to play with and provides a good behavior space exercise, it is really not a good example of the kind of problem that requires an ABM to understand. So let's move on to a model that is, in contrast, a classic example of emergent dynamics. Another model in the biology section of NetLogo's model library is the flocking model. This is a NetLogo version of a well-known example of how complex and realistic dynamics can emerge from a very few simple agent behaviors in ways that could not be completely predicted. Schools of fish and flocks of birds can be thought of as emergent properties of how the individual animals move in response to each other. A school or flock can appear as a coherent entity, but it can also break up and reform, and its shape changes continually. In the flocking model, the individuals have one behavior, adjusting their movement direction in response to the location and direction of other nearby individuals. They make this decision considering 3 objectives: moving in the same direction as their flock mates. We call that align. Moving towards the flock mates, which we call cohere. And maintaining a minimum separation from all other individuals, which we call separate. Parameters control the relative strength of these 3 objectives by limiting the maximum angle a turtle can turn to align, cohere, and separate. The minimum separation parameter sets the distance at which turtles try to separate from each other. You will quickly see that the flocking model's results are in fact pretty complex. The turtles form flocks that continually change characteristics, and these characteristics change as you vary the parameters. Further, parameters seem to interact. For example, see what happens when you vary max cohere turn when minimum separation is low, then high. In fact, the flocking model demonstrates 2 common, though not universal, characteristics of emergent dynamics. First, the most important and interesting results of the model seem qualitative and hard to describe with numbers. Whereas the state of the simple birth rates model can be described by 2 numbers, that's how many red and blue turtles are alive, the characteristics of the emergent flocks clearly change as you vary parameters, but in ways that are not easy to quantify. Second, it takes some time before the flock characteristics emerge, both when the model starts and when you change parameter values in the middle of a run. ABMs often have a warm-up period in which their dynamics gradually emerge. So, is the flocking model emergent? Absolutely. Let's run the model. And here I've sped up by setting execution from ticks to continuous. We can see here that flocks form without a leader. Since we're not using any random numbers except to position the birds initially, the behavior of the birds is produced by deterministic rules. We are also seeing that each flock is dynamic. A flock, once together, is not guaranteed to keep all of its members. Look at the calculations we can perform in the box on the right side. Why would, after running the model for a while, all of the birds have approximately the same heading? It seems that we will want to perform a number of runs in sequence, so we will want to use replicates. We want to get output from every tick of model runs that are over 500 ticks. We set up our baseline scenario with the default parameter values and then run 10 replicates of the scenario. And as we set up the behavior space, we need to be prepared for a runtime error. Now look at the code in the bottom left corner here. The experiment uses the turtle variable flockmates, which is the agent set of other nearby turtles. So behavior space calculates its first output when the setup procedure has finished before the run starts. However, at this point, flockmates has not yet been initialized, so NetLogo does not know that it is an agent set. We need to solve this by initializing flockmates. To do so, we need to add the statement set flockmates no turtles to create turtles in our toSetup procedure, and that is highlighted right here. All right, time to talk in more depth about the methods to set up behavior space. Let's go back to the red-blue fertility model. To set up behavior space, go to Tools, then pick Behavior Space and select the New button. This will open up the experiment window. We will name the experiment Blue Fertility. We want to vary the following variables: Blue Fertility starting at 2.1, then incrementing by 0.1 in each run until we have reached a value of 5. Red Fertility setting to 2, and we're setting the carrying capacity to 1000. We will set the repetitions to 10. That's 10 replicates. And we will need to fill in the measure runs using, etc., etc. Then we need to specify the desired result, which is the tick number at which the red turtles become extinct. So we're telling the model to stop when the number of red turtles is 0, and we record the output tick number with NetLogo primitive ticks. So we're putting ticks in the measure runs field and uncheck measure runs at every step. To see where red count is calculated, we go to the interface and we right click on the plot, and you will see when you do that, that the red count is calculated in the pen update commands. Once we have run the model, we can save the output in a CSV file as you're seeing on the right side, from which we can build a pivot table in any spreadsheet app. Here you're seeing my table in Microsoft Excel. And here's the detailed solution path to determine the effect of blue fertility on red extinction. You're seeing the behavior space set up on the left and the run options I have selected in the middle. Note that I've selected both spreadsheet and table output. This will write 2 CSV files into a directory on my computer that I can specify. Now I can use pivot tables to process my output, no matter whether in Excel to the left, LibreOffice in the middle, or Google Sheets on the right-hand side. Here you're seeing my pivot table setup. Note that to find the average and standard deviation, you will need to select the expander to the right of sum of ticks and select standard deviation in the pop-up. Then hit OK to save. All right, here's a summary of what we've discussed in this module. We've learned that simulation models can reproduce how complex dynamics of real systems and complex agent behaviors emerge from the characteristics, behavioral traits, and interactions of the system's members and their environment. We've learned that ABMs can range from having predictable results that are imposed by simple rigid rules for agent behavior to producing complex results that are very difficult to predict from agent behaviors. When we want to describe the emergent characteristics of an ABM, we start by defining what the key outcomes of the model are and the agent behaviors that those outcomes emerge from. We also need to describe how model outcomes emerge from the agent's environment, if they do. And making model results more emergent is not always better. Simple ABMs with imposed dynamics like the butterfly model can still be useful and appropriate for many problems because they are easier and more intuitive to build and understand than equation-based models. At the other extreme, an ABM with emergent outcomes so complex that they are unpredictable would be very hard to use for science because our goal is to figure out what underlying processes cause the emergent outcomes. So models such as flocking that merely demonstrate emergence are not inherently scientific. However, they can be put to scientific use when, through simulation experiments, we are able to understand some specific emergent properties of a real system. And we observed two common characteristics of emergent dynamics in the flocking model. First, important emergent outcomes may seem more qualitative than quantitative, but we can find numerical outputs to describe them. Second, it often takes a considerable warm-up period before emergent outcomes become apparent and stabilize. And here is what you have learned in this module. Pause the video for a moment to read through these items and ensure that you're comfortable with everything on this list. Thanks for watching. I look forward to seeing you again in the next video.